Hey there, geometry. We are in lesson 7. In lesson 7, we're actually going to talk about angle side angle triangle theorem. Pin. So angle side angle, which we've done before, and here we're talking where our side is included in between the two angles. All right, so I introduced all of these theorems to you, I believe, back in lesson 5, but in lesson 7, we're actually going to practice with them a little bit. So to start off here with our first little task, notice and wonder. I'm going to read this and then we're going to go over to GeoGebra to play with it a little bit. So the assertion is, through two distinct points passes a unique line. So AP and QB, two lines are said to be distinct if there is at least one point that belongs to one but not the other. Okay, so A belongs to line, so I look at A, it belongs to line L, but not line M. That's an M. M. Line B belongs to line M, but not line L. So that's what a distinct point is. Otherwise, we say the lines are the same. Lines that have no point in common are said to be parallel. So no point in common means they're parallel. Therefore, we can conclude, given two distinct lines, either they are parallel or they have exactly one point in common. This is almost true, okay? First, let's go over to GeoGebra and play with it a little bit. So here we are. Now, line L has point A on it. Line M has point B on it. But what I can do here is pull these apart. So here they're not, they don't have an intersection point, but they do. If I were in the real GeoGebra app, I could mark this intersection with another letter. But what's really cool is I can pull these apart and there's no intersection, therefore they're parallel. At least one intersection, therefore they intersect. But it's really crazy, and I'm going to show my hands here for a moment. Like, what you're seeing here are two lines that are parallel. Okay, they're parallel because they're in the same plane, and the plane is going up and down like this. So these two lines are parallel, but they share one plane, cutting up and down here. Now, what if I go like this? They're not intersecting. There's no intersection point between these two lines. But there's also no plane that they share. They must share a plane for them to be parallel. So here's parallel. Here's two distinct lines. They intersect. But this is called skew. Okay, that's a big difference. That is called skew. And I can't write on this page, but that's what I wanted to show you. Let's go back here. All right, so proving the angle side angle congruence theorem. We're going to go over to GeoGebra again here in a second, but here's my student task statement. Two triangles have two pairs of corresponding angles congruent, and the corresponding sides between those triangles are congruent. That one is our included side, okay? Sketch two triangles that fit this description. So we're going to go over here. Hold on a second. Now I could sketch two triangles that look like this and mark them. Side, side, angle, 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 angle. And that is side, angle, side. Okay? Nope. We're doing angle, side, angle. Eraser. Ooh, big eraser. Angle, side, angle. So two angles are congruent, two sides are congruent, two angles are congruent. But let's construct it. I want to practice this construction really quick. So if I come over here, hold on, let me shut this little guy down because he's bouncing. I'm going to construct a segment. And then I'm going to construct an angle. I'm going to make it super long. And then I'm going to construct an angle. And again, super long. Now what I want to do is make two triangles. Let's move, oh no, undo. Let's make this one really wide. All right, so I'm going to have my triangles, this be a shared side. I like to reflect this angle over to this side and reflect this angle over to that side. Okay, so I need more angle. Let's measure this angle. So I want to copy this angle. So I'm actually going to transform reflected about a line. So if I reflect this segment over that line, I get another angle. Let's measure this and show that it's congruent. Cool. Now I'd like to reflect this one over there because when I reflect something, I make something congruent. Transform, reflect about a line. Cool. Now, measuring these angles doesn't always work out. Let's see what happens. Yeah. For some reason, I can't measure the internal angle, and I don't know how. Like, I can't get that angle to go on the inside. So I do know that to find that internal angle, to find this angle right here, there's just no way for me to do it. I've tried. I don't know what I do wrong. Yep, that didn't work. I copy it from one side to the other side, doesn't matter. I would take 180 and subtract 123.4, okay? And that is 6.6. That would give it 130, 56.6, I hope, because we're going to measure this one. Yay! I can't always do math in my head, and when I do, sometimes I'm right, sometimes I'm wrong. So this angle is 56.6, that angle is 56.6. So we have constructed a congruent angle, congruent side, and congruent angle. So we did ASA. Now, let's test it. Let's see if the other two sides are congruent. All right, I need to mark that, nope. Where's my points? I need to mark the lines, conics, polygons. I can never find the gosh darn intersection. There it is. Whew. Because I need to mark where these two things intersect. Okay? Because that's the only way I can measure them. All right, so I'm going to measure A to E and A to F. Both 5.8. Woohoo! Okay, E to B and F to B. Woohoo! Ooh, let's see if the angle's the same. Okay, last time I did this, I did not, nope. I did not check the angle well, or I didn't check this angle. We know that it's going to be congruent because the angle addition theorem tells us that the inside of an angle adds to 180. So if this angle up here is 96.2, then this one is 2 because they are vertical. Okay, you got it. And that should be the same as this one. I'm not sure which one is going to measure. Okay. 96.2 is that internal angle also, and we know that because they're vertical. All right, so we have everything measured. Life is grand. I'm going to actually write out this proof. So let me go back over to OneNote. I actually want to make some more space, and I haven't been that good at this. I believe I just want to go like this. And it's going to add some space. It didn't work. Insert space. Oh. Huh, how did I do that before? Okay, it's not working. Okay, I'm sorry, and now I'm wasting time. I know I am. So let's go over here. I'm going to make this a little bit smaller and take a picture. And I know I'm going to put that into Notability or into OneNote, and it's going to be huge and hard to get in, but it's okay. Copy into OneNote. Let's just put it down here. Oh, looks like that's where all the space went. That's pretty funny. Putting it right here. So we got it in there. Let's just write a basic proof. All right, we're going to go with the things that were given. We know that angle, this up here is an E. E, A prime, B prime is congruent to angle F, A prime, B prime. We also know that side A prime, B prime is congruent to A prime, B prime. Okay, those are both segments, and we know this is true because it's given, and this is true because it's given. Given. Oh my. Yeah, I can spell. Let's try that again. You could also say it's the same, or you could say it's reflexive. Either one works. And then we're going to go to the other angle. We have E, B prime, A prime is congruent to F, B prime, A prime because it's given. Okay, we just did angle, side, angle. So now I can say that triangle E, A prime, B prime is congruent to triangle F, A prime, B prime because of ASA. So we just did a really basic and simple proof, right? Cool. I didn't even read the rest of these, so I did not label the triangles that they wanted to. So the angle W is congruent to angle D. We know they're congruent because that's the first and the first, so that is angle W and angle D. And then angle X is congruent to angle E, which is fine. And side WX is congruent to side DE, which is great. And then use a sequence of rigid motions to take triangle XYZ, WXY, to triangle DEF. We don't need to do that because we used rigid motions to construct our triangles, and that's fine. But let's go ahead and look at these two activities. I'm not going to, well, we can. I'm getting rid of half these letters though because it's way confusing. I can see that these two angles are congruent, these two angles are congruent, and those sides are shared. So I can say angle YDE is congruent to angle FED, and we can say that's given. Side DE is congruent to side DE because they're the same, because it's reflexive, because it's given. And then, let's see, we did YDE. So now we needed YED is congruent to angle F. Let's see, we did YDE. Oh, we already, no, YED, so we want FDE. We have to say them in the right order, or it won't work. So now we can say that triangle YED is congruent to triangle FDE because of angle, side, angle, all right? Same thing here. I'm not going to write it out as much, but I will highlight the things. So I have angle A and angle C, side AE and CE, AE and EC, and then that angle and this angle. Therefore, those two triangles are congruent because of, that's a really thick marker, ASA. Cool, let's move on. Look at all that space I made. All right, find the missing angle measures, optional. Okay, this won't take long. We're gonna find the missing angle measures. We know that line L and M are parallel. I'm gonna mark them like that. So I can say that line L is parallel to line M, and that's given. We have angle A equals 42 degrees, and that's also given. Now we want to find angles B, C, D, E, E, F, and G. We're going to find them all. Well, angle A is corresponding to angle E. And I know when two lines are parallel, corresponding angles are congruent. I know angle A is vertical with angle C, and vertical angles are congruent. Now angle C is corresponding to angle G, so that's congruent, but angle E is vertical to angle G, so that's also congruent. So I could have found angle G in two different ways. Now, how do I find the others? If this is 42, I know it's a linear pair with A. So A plus B equals 180. So if A is 42, if I just substitute there and then subtract from both sides, I would get 136. So angle B is 136. And here we have vertical, corresponding, and D to F, alternate interior, or corresponding, or vertical. All of them work. Okay, we found all the angles. Good job. Now this last thing, we rarely get 4 things to do in one lesson. Today we do. What do we know for sure about parallelograms? So parallelograms, the opposite sides are parallel. So that's an arrow, this is a double arrow, and that's a double arrow. Because we have opposite sides being parallel, we know MNKL is a parallelogram. So our student task statement says quadrilateral ABCD is a parallelogram. Okay, we're going to just ignore this for a second. We're working on this task statement, and it doesn't have anything to do with this activity synthesis, okay? So quadrilateral ABCD is a parallelogram. By definition, that means segment AB is parallel to segment CD, and segment BC is parallel to segment AD. Sketch a parallelogram and then draw an auxiliary line to show how ABCD can be decomposed into 2 triangles. So if this is a parallelogram, we always go in a roundabout order, A, B, C, D, always. I know these 2 are parallel, and these 2 are parallel. So I can draw an auxiliary line to help me prove that the triangles, I just decomposed it into 2, and then I can prove that they are congruent and explain why. So what we can do is this auxiliary line that we drew, I'm going to extend it a little bit so that it's easier to see. And then I'm going to extend these lines a little bit so they're easier to see. So that red line is really a transversal, which means this right here, let's go blue, this angle and this angle are congruent because they're alternate interior angles. So first I can say that AB is parallel to DC. And then I can construct BD just for an auxiliary line. Sorry, this first one is given, and this is my auxiliary line. All right, move this up a little bit. I can say that angle ABD is congruent to angle CDB because when 2 lines are parallel, the alternate interior angles are congruent. Cool? All right, now I'm going green. If I extend this line and this line, it actually can be easier to see. And then I turn my head like this. I can see that this angle and this angle are alternate interior angles, okay? So I can say that angle ADB is congruent to angle CBD for the same reason as above. That's just that little like look above, you know, ditto, right? Because I don't want to write it again because I'm lazy. So that's cool. And now I can say that those segments are congruent. DB is congruent to DB because reflexive or the word same. Okay. And now I have angle, side, angle. I can say that triangle ADB is congruent to triangle CBD because angle, side, angle, congruency theorem. Woohoo! We did it. Is that what we were supposed to do? Yes. Good. Explain why that shows one pair of opposite sides of a parallelogram must be congruent. So this last part, part 2, is super duper important because we just proved those triangles are congruent. Now it's asking us to use that to prove that the opposite sides of a parallelogram are congruent. So AB and DC are opposite sides. They're congruent. We know that. I can say AB is congruent to DC because CPCTC. Congruent parts of congruent triangles are congruent. Because we proved the triangles are congruent, we can say the opposite sides are equal. That's the same with AD. That's an A. AD is congruent to BC, CPCTC. I can say these are congruent. I can also say those angles are congruent, okay, because of CPCTC. I'm out of space. Okay, angle A is congruent to angle C. Everything's congruent. It's a parallelogram because of CPCTC. All right, that was fun. Activity synthesis. Again, I've got opposite sides are congruent, opposite sides are congruent. I'm going to mark this and make it congruent. Therefore, I can say triangle NML is congruent to triangle NML LKN because of side, side, side. Now, I know that because I did that, I know that this angle and this angle are congruent because of CPCTC. I know that this angle and this angle are congruent because of CPCTC. And because those angles are congruent, we can say the lines are parallel. Okay, when alternate interior angles are congruent, we know the lines are parallel. It's called the converse of what we did over here. Over here, we knew the lines were parallel, therefore the angles are congruent. Over here, we know the angles are congruent because of CPCTC, therefore the lines are parallel. Very cool. I hope you watched to the end of this lesson to get that part. And that's it for today. Good job.